We've spent decades, literally decades, imagining what other worlds might look like. But what happens when you finally see one with your own eyes? And I don't mean an artist's rendering or a computer simulation. I mean a real, actual photograph of an alien solar system. In today's Explainer, we're breaking down some absolutely mind-blowing leaps in astrophysics that are completely rewriting our understanding of the cosmos. And we're going to kick things off with the stunning HR 8799 system. Now, actually spotting these worlds requires overcoming a massive physical hurdle, which is the blinding glare of the host star itself. Think of it like trying to spot a dim little fly buzzing right next to a towering, bright lighthouse from miles and miles away. That is exactly the challenge astronomers face when they try peering into these distant cosmic neighborhoods. And to make matters tougher, HR 8799 sits 130 light years away. To put that sheer distance into perspective, the photons of light our telescopes are capturing right now, they actually left that star before World War I even began. So bridging that vast gulf to resolve something as tiny as a planet requires an absolute masterclass in optical engineering. But using the incredible power of the Keck Observatory and the James Webb Space Telescope, astronomers achieved the impossible here. We didn't just detect shadows or little dips in starlight like we usually do. No, we directly imaged 4 massive gas giants. We can literally trace the orbital paths of these giant worlds over time, giving us a front-row seat to a real alien solar system in motion. To pull a feat like this off from the ground, astronomers rely on something called adaptive optics, which is an absolute game changer. It basically counteracts Earth's wobbly, turbulent atmosphere in real time. It does this by rapidly computing and then physically deforming the telescope mirrors thousands of times every single second. The result? We get images at near-infrared wavelengths that are amazingly 3 to 4 times sharper than even the Hubble Space Telescope. And this technology is evolving so fast. The upcoming Nancy Grace Roman Space Telescope is going to feature a coronagraph that uses a really fascinating physics trick called destructive interference. It actively creates an opposite wave to the incoming starlight. By matching the light peaks with opposite valleys, it literally cancels out the star's glare, wave by wave. This clears the field entirely, revealing planets that are 1 billion times fainter than their host star. Once this incredible tech finally gives us a clear view, we start finding worlds characterized by absolute extremes. Take the hot Jupiter exoplanet WASP-94ab, for example. James Webb revealed a totally bizarre daily cycle there. Intense morning winds gather these thick clouds made of magnesium silicate, which means literal rock clouds. But then, as day turns to evening, the scorching heat completely vaporizes them, leaving clear skies behind. Imagine that, a daily weather cycle of gathering and dissipating rocks. Wild, right? Observations like these are actively forcing us to tear up our old astrophysics textbooks. Just recently, astronomers discovered 4 strange gas giants orbiting their stars at least 4 times closer than Mercury orbits our sun. According to traditional physics, a planet shouldn't even be able to form that close without being ripped to shreds by radiation. And yet, here they are, totally defying all our models. And this actually forces us to rethink our own cosmic backyard, too. Even our king of planets, Jupiter, likely wasn't born where it sits today. Advanced models are now showing that its early growth was fueled by something called pebble accretion, basically rapidly gobbling up material in the early solar system. This caused a chaotic, violent tinward migration toward the sun. That kind of massive planetary reshuffling would have spelled disaster for any other infant planets caught in its path. Sticking a bit closer to home, we've seen firsthand how violent stellar forces can completely alter a planet's destiny. NASA's MAVEN orbiter actually proved that Mars lost its ancient warm and wet environment because brutal solar winds have literally stripped its atmosphere away over time. Because it lacks a protective magnetic field, Mars loses about 100 grams of its atmosphere every single second, just getting splashed away by heavy solar ions. But while we track the histories of our local planets, we're also keeping our eyes peeled for ancient transient visitors zooming through our system. In what was an incredibly rare event, the interstellar comet 3I/Atlas was captured from 2 different angles simultaneously. The Europa Clipper spacecraft observed the scattered dust on the comet's night side, while the JUICE spacecraft managed to image the glowing gas on its day side at the exact same time. Of course, to map the very edges of our local neighborhood, we've had to rely on epic legacy missions like Voyager. Launched way back in 1977, Voyager gave us our first detailed looks at Uranus and Neptune. And then, in 2012, Voyager 1 achieved the unthinkable. It pushed past the solar wind boundary to become the very first human-made object to cross the heliopause and enter the dark, intense radiation of true interstellar space. Now, zooming out to the absolute deepest cosmic scales, way beyond our galaxy entirely, we have to rely on a mind-bending trick of physics called gravitational lensing. When a massive cluster of foreground galaxies sits between us and a distant object, its immense gravity actually bends and stretches the background light. So nature is essentially providing us with a literal cosmic magnifying glass. This lets us see things at the dawn of time that would otherwise be entirely invisible to us. And the James Webb Space Telescope recently used this exact natural magnification to achieve a massive first in astrophysics. By combining JWST's incredible infrared sensors with one of these gravitational lenses, astronomers were able to track the movement of individual stars to actually weigh a dormant black hole. And we're talking about a black hole sitting inside an early galaxy, a staggering 10 billion light-years away. To capture a universe this massive and ever-changing on a continuous basis, we need unprecedented tools. Enter the Vera C. Rubin Observatory down in Chile. Utilizing a massive 8.4-meter mirror and a frankly staggering 3.2 gigapixel digital camera, it is going to map the entire visible southern sky every 3 to 4 nights. This is basically going to create a decade-long ultra-high-definition time-lapse of the heavens. But here is the most humbling realization of all. Everything we've discussed so far, the planets, the stars, the comets, the black holes, all of that makes up just 5% of the universe. The Rubin Observatory's primary mission is actually to hunt down the other 95%. And that 95% consists entirely of invisible, mysterious dark matter and dark energy that we know for sure is out there, but we still don't fully understand. As you might guess, the sheer volume of data required for this hunt is totally staggering. In just a single test night, the observatory's automated system generated 800,000 alerts for objects that either moved or changed brightness. When it's fully operational, it's expected to max out at around 7 million alerts every single time the sun goes down. It's creating a real-time discovery machine unlike anything humanity has ever built. As the team that weighed that ancient black hole noted, this new era of observation is proving that the universe is far more beautifully structured and interconnected than we ever imagined. From the violent migration of early gas giants all the way to dormant black holes 10 billion light-years away, the pieces of this giant cosmic puzzle are finally starting to come together. Which really leaves us with one final thought. As our technology rapidly peels back the cosmic darkness, from directly imaging alien solar systems to tracking billions of galaxies in real time, we are moving from simply observing the universe to truly understanding its hidden mechanics. If we've discovered all of this in just the last few years alone, what impossible worlds do you think we'll find tomorrow? Thanks so much for exploring the cosmos with me on today's Explainer, and I'll catch you next time.